And the next presentation is a co-presentation with Alex Giladi, and he is a distinguished architect at Comcast, where he works on various aspects of end-to-end content distribution and adaptive streaming ecosystems. He worked on architecture, implementation, and standardization of various stages of video delivery pipeline since 2000. And we start with John Ellerton, and he's the head of the future and innovation at BT Media and Broadcast, and he's the chair of the SMT UK. Welcome, John, and later, Alex.
Now? You can hear me now? Okay, I'll start here. All right, the last talk before the drinks reception. So let's try and keep the momentum going. Are we going forwards or backwards? We're going forwards. There we go. All right. Let's start off with something a little bit provocative then. The switch off of digital terrestrial and satellite TV is coming fast. Well, it is in some countries around the world, and certainly in the one that I live in the UK. The Director General of the BBC is on record talking about the future of television being streaming. And in some years, we don't quite know how many years, but in some years' time, we will switch off traditional TV in the UK, and that's going to happen in other countries around the world. New Zealand, I found that when I was Googling around earlier on, have said the same thing. So we need a truly scalable architecture to deliver TV to millions of consumers over the internet with the same latency, stability, and the performance that they're used to over an entirely different technology stack. So this presentation that I'm doing along with Alex over there talks about a suite of technologies that aims to solve this problem, but it also talks about a collaborative project, an IBC accelerator, that we've run for the past 2 years. We're co-champions of this accelerator with a bunch of other people in the industry who are all listed on the slide here to prove it. And we ran it at IBC 2024 on a small scale, and then we went bigger at IBC this year to demonstrate that it actually scales globally. So the presentation will talk about what are the goals, what's the current problem in terms of latency, why does it take so long to get pictures to consumers over the internet. Then Alex will talk about the foundational technologies, and then what we actually built and proved. So the technical goal, well, in 1969, the moon landing was broadcast. It had a 3-second latency all the way from moon and 650 million viewers. Fast forward to last year, and the Super Bowl was broadcast, and it had an over 40-second latency and 120 million viewers. It feels like we're going backwards here in terms of latency performance. So it's only going to get worse, isn't it? As we try to scale the infrastructure out, unless we do something. So we need to build a blueprint, as it says here, for a viable production system built on open standards which can scale, and the aim is to achieve the latency that is of a similar grade as digital terrestrial television, whilst allowing at the same time personalized advertisements and the monitoring performance using precise metrics. So technologies, L3D dash, server-guided ad insertion, the dash alternative MPD, and for telemetry, CMCD version 2. And Alex will describe what each of those are. Why is live not live anymore? I'm sure most of you in the room know this stuff already, but let's just talk about it very briefly. If we go from camera at the left-hand end to the display device at the right-hand end, we concatenate encoding. We start by doing contribution encoding to get from the venue to the broadcast center. We multiplex it together. We do contribution links using SRT. All of that adds up. Then we make the program, and then we distribute it. We do encoding for distribution. We multiplex it. We then package it up to go over the internet. We do propagation through CDNs. We send it to the player that has an enormous buffer, be confident is going to play out reliably. There must be a better way. Alex, come tell us. What's the better way?
Thank you, John. Can you hear me? Okay. So let's see how we can make live again. So There are a couple of things that are probably the easiest and are being done. The first thing, let's go and pipeline the delivery, which is also known as low latency dash and low latency HLS. So let's say in the previous diagram we had 2-second segments, pretty common. So instead of going and accumulating 2 seconds worth of media and then sending them all at once, let's do a revolutionary thing. Let's accumulate, let's say, 100 milliseconds, send them, next 100 milliseconds, and so on. So what you'll get is you'll be able to decode the first frame of the segment before the last frame of the segment actually entered the encoder. If you don't know about MPEG-2 transport stream, this is revolutionary. But then, since our buffer, so the long buffer that we're looking at, that was like 14 seconds, it can be smaller because it's actually in delivery units. And we're delivering not in units of 2 seconds, but we're delivering in units of 100 milliseconds. So this is something that makes a very significant difference. Next is the encoder itself. So this is extremely specific to each implementation, but initially people used to use 8-second encoder latency. Latency being from an input to an access unit on the output. Turns out that you can do with significantly less than that. We haven't seen any problems with something that is, let's say, 3 seconds, and you can pay a little bit in compression efficiency and go as low as 2 seconds or sub 2 seconds. So these two bring us to already a much better experience, and you can actually see things like this being deployed. So then the question is, can we shave off even more? So the first thing is reduce contribution delays. If you remember the moon example, the contribution delay there was most of these 3 seconds. Can we cut something there? We're not on the moon. And the other part, let's try reducing the encoder delay. Let's reduce video start time, and we'll talk about it later. And then, contradicting everything I just said, let's not live dangerously. If we saved something, let's share and give a part of it to the player, because the longer the player buffer, the less rebuffering events. So the first thing that we did was edge encoding. What it does roughly is we eliminate contribution. We encode the full ABR ladder for distribution next to the playout. So this does a couple of things. First of all, this reduces latency. It improves the quality, and it requires less bandwidth if you care about bandwidth on your playout to the origin hub. The thing that makes it possible is -F live ingest, which is a pretty intellectual protocol. It just goes and pushes chunks, CMF chunks, up using HTTP post. So what this does, if we compare it with normal transport stream, it eliminates the maxing delay. You typically want to output TR101 to 90, nice constant rate, and you spend a while, at least a second, in going and making sure that your rate is constant. You don't care because the flow control here is handled by the transport layer, TCP, or in case of HTTP3 by QUIC. Next technology is low latency, low delay, or L3D dash, and it has two aspects. One is instead of having a flow of chunks, we individually address partial segments, and the second thing is we're doing low delay using short gaps. So the first one, low latency dash, well known, uses chunk transfer encoding to send individual CMF chunks. What this means is you request a segment, then you get chunk 1, then you get chunk 2, chunk 3, chunk 4, and this is the end of your GET request. So there are two problems with this approach. One is the transport stack, especially in browsers, is unaware of the meaning of the bytes in it and the meaning of the boundaries of CMF chunk. So you can have the end of your chunk stuck in some layer of buffering till the next one arrives. So this affects your latency. The other thing, for the same reason, it's much harder to go and measure the available throughput. So we took the low latency HLS approach of addressable partial segments, which means that we are fully compatible with low latency HLS here. However, as usual, we are slightly more efficient. Dash templates, Dash predictive templates let you guess what would be the URL that you need to request without having it listed as you have an HLS. So this means that even if we go and provide partial segments every 100 milliseconds, you still need to go and download the manifest every 2 seconds, and if you do some smart things, even less than that. Fast tune-in, typically you cannot tune in at a granularity smaller than the GOP boundaries, but this can be fixed by introducing a special purpose representation. We know that it is compression-wise inefficient. We're doing very short GOPs, low resolution to save bandwidth, and we only use it in order to start playback, to seek or to return from unconditioned DAI. So then, once we get going, we switch to a normal general purpose representation, which is what I'm going to show now. So we started at some random place, and the example here is we're using 6-frame GOPs and 6-frame segments. We go and start playing them until we get to the segment boundary of the more efficient representation that has 24-frame GOPs. We switch to it, just normal rate switching, nothing special, because they all start with ADRs. Then we continue playing until we get to the regular segment that we actually want to play, which is normal 2 seconds. So at the worst, you are using inefficient representations for slightly less than 2 seconds. Now this all is good, but somehow we need to measure and to quantify things. And first time I ran into Common Media Client data, the CMCD spec, was when I was trying to debug my first low latency prototype, and it provided a ton of invaluable information, for instance, about the buffer behavior. So since then, I really love this spec and participate in it. What it actually does is it standardizes the metrics, how they're derived, and how they're transmitted on the wire. Yes, you can do it with proprietary products, but the good thing is here, it's an interoperable standard. So what it does is buffer level, rebuffering, playhead position, latency, video startup time, video start failure, a URL of the next request, time to first last byte, so the classical CDN metrics. And there are 2 modes in which it requests them. We'll go over them in a little bit, but hand waving level, the first mode is piggybacking on an HTTP GET request. So you are requesting a video segment, and you are also using headers or query parameters to pass some information. The other mode is an event mode. You post at a given time a bunch of information to a collector URL. So here is the request mode. You want to go and in the specific case tell how much media you have in a buffer. So you create a CMCD string, you go and append it to the video segment URL, and you send it. So CDN happily replies and also logs the URL and the headers. And then it ships these logs to an analytics endpoint where you can go and analyze this. The event mode, slightly different, same interaction with CDN, but then triggered by either the request or a player event, let's say somebody pressing play, or a user action. You go and post information about your current state at a given timestamp. And why are we doing this? A couple of things. First of all, it's much better for analytics because your latency in terms of information getting into your processing pipeline becomes at most seconds instead of minutes. When we're experimenting with the previous mode, we had a CDN who actually gave us a 30-minute delay, which makes anything real-time useless. And then there are no CDN dependencies because it's pretty pointless to go and tell a CDN when it's dead that it is dead. You won't notice. Last thing, add insertion. Typically, it wouldn't have belonged here, but unfortunately, the unicast nature of streaming allows personalized targeted advertisement. Anything personalized for a large enough scale is a horror story. So server-guided ad insertion is currently considered the most scalable methodology. And next, we'll first very quickly go over the history and the definition of server-guided ad insertion, and then deep dive into how it is implemented. And I promise you that's the last deep dive before the drinks. So going 50 years back, we used to have analog video, and we had the MTF tone transmitted in audio, and it was activating a VCR, which was playing a prepared ad tape, and then it was told to stop, and the signal returned back. A little bit later, we had MPEG-2, and we replaced the MTF with SCSI-35 Q messages, and we introduced a concept of a splicer, which would respond to these messages, same as VCR would, ask an ad decisioning system, which ad should I play in Pasadena, given that we have a 42-second opportunity to do so. The reason I'm mentioning Pasadena, beyond the fact that we're here, is that this is the degree of targeting that was possible. Now came streaming. Everything changed. So we're doing exactly the same thing. We're sending a manifest, MPD in dash terms, to a manifest manipulator. It carries SCSI-35 Q messages. The manifest manipulator talks to the ADS and says, which ad should I play to John, given a 42-second opportunity? The difference is that since this is unicast and we know who requested the manifest, we can go and prepare a personalized manifest with ads already inserted. So it's rock solid. It's awesome. The only problem is that it doesn't scale, because the compute here is linear to the number of viewers, and the manifests are personal and as a result are not cacheable. So something entirely different, client side. Let's go and move all of the compute to the client and make the manifest scale, make a manifest cacheable. So a client has an ad module, what used to be the splicer. It reacts to SCSI-35 Q messages. It consults in some way, we don't know which, with an ad decisioning system. So you need some integration. Commonly would be doing a BVAST or something like this. Client plays and terminates an ad. Possibly it uses a second player for the ads, and it does beaconing to prove that an ad was actually played. So seems awesome. Couple of problems. It's complex, it's fragile, and every deployment needs bespoke client-side development on multiple platforms. So as a result, people arrived at server-guided ad insertion, SGAI, which is the best of both worlds and more similar to client-side. So server maintains single manifest with triggers, same as before, but we swap out SCSI-35 for a new type of trigger. So SCSI-35 is a great thing, but it describes where to insert and for how long. It is not actionable. So what we need is something that contains precise instructions. Here is the URL, issue an HTTP GET, then here is the format you should expect, and here is what you know what to do with it. So as a result, we have a trigger processing that is fully interoperable, and we have an endpoint, an SGAI endpoint, which is an intermediary, and it does a translation from, let's say, Dash or HLS into, for instance, VAS to talk to an ADS. And this is where the business logic lives. And then how this is actually implemented in Dash. In HLS, it's implemented as interstitials. In Dash, this is implemented as events. And the meaning of an event is a blob in the MPD in the manifest that says, start playing another MPD that is available at this URL and come back to the main one, either when you are done or when we tell you otherwise. So We have URL, we have timing information, and we have directives like please don't repeat this ad if you encounter it in time-shifted domain. The second concept is list MPD. So this is a dash representation of an ad break. So it's basically a dash formatted list of ad URLs and some additional beaconing information, maybe something else related to CDN and failover. It can be generated in memory out of the VAST response, for instance, in an SGI endpoint. For VAST to MPD, there is actually an open source project that already does this. And then there is a process of merging. How do you actually coalesce the multiple ad MPDs into a single break? And this happens in a client, same as it would have been in case of client side. Last thing actually doesn't belong to either MPDs or events. NXI is how do you decorate outgoing HTTP requests, either with query parameters or headers, and how do you push either pass-through information or state such as coded language and so on forward. And you can do this, and the SGA endpoint conveys the state to the decisioning system. And for instance, this means that if you are playing H.264, you'll get an H.264 ad, not an HEVC or AV1. How does the alternative MPD replacement event work? So first of all, the event arrives. Arrives is you update your manifest. You are doing it at the worst case every segment. And all of a sudden, you have a new element that is called alternative MPD replacement. You see this, you process this. Eventually, playback starts after you have prefetched, and we'll talk about it later, the actual ad. When the playback starts, the main client enters listen mode. In the list mode, the client updates the MPDs, it processes events, but it never renders anything. It can decode if it wants to. So de facto, it's just a control channel. Then the main presentation is resumed, either when the ad is over and alternative presentation ends, or when we tell the presentation to stop, which we'll discuss right now. So prefetching is pretty key functionality for scalable ad insertion. Why? Because typically, you know precisely when the ad is going to come, only 4 to 8 seconds before it starts. So there is a huge thundering herd of requests for ads. And then remember that it's not really well cached as they are targeted, and you need to talk to the ATS before even knowing which ads you're going to fetch. So events and alternative events can be updated. So as a result, you can change timing and duration, you can postpone, or you can cancel the event. So this is the side effect that we're using here. So let's say the first time we see an event, it tells us, okay, there is an ad break somewhere in 1 minute. And it tells us when we can go and prefetch the alternative MPD. We randomize the time at which we prefetch, and the curve is, let's say, flattened to 1 minute. We process the list MPD. If we get it, we prefetch all the resources. Then, in parallel, we get another event update that says, oh, and here is the actual precise time at which the break starts. So by that time, you already have everything you need, and you can start. You may not necessarily know when to finish. So yet another update, which can happen even when you're playing the ad, will tell you this is your maximum duration. And if the main client discovers that the alternative presentation went over its duration, it will kill it. So this is how you do return to network, or if you start an ad break and you don't know how long it is, this is how you go and fix this issue. So putting this all together, and apologies, that's too many lines before drinks. So you have a client. The client, in the beginning of time, asks for an MPD. It gets a 302 redirect to a main MPD plus ID equals 42, which is just a pass-through parameter. Nobody knows what it is. And then you will keep requesting MPD with this ID, and you will also know thanks to an XI that there is a parameter named ID, and you can go and append it to other URLs as well. So we see an event that tells us ad break coming in a minute. We go and construct a URL. This is the alternative MPD URL plus the pass-through parameter ID plus the fact that we're playing in English. We combine all of this. We go to the SGA endpoint and ask it to give us the ad break. It talks to the ADS. ADS responds. We get the list MPD. We go and resolve the list MPD. In parallel, event is updated. We start playing that list MPD. Main client is in listen mode. It gets an update that says, okay, your duration is 0. So this means the alternative presentation is immediately terminated, and you are back to the main content. So we actually put all of this together over a few months this year and demoed it at IBC25. So RT, the Irish public broadcaster, provided us a couple of sources. They went to a live distribution encoder, which pushed segments using -F live ingest in units of 480 milliseconds. It pushed it to the origin, then CDN, then flare, regular L3D dash. Unfortunately, we had to do an ugly hack, and we had to do manifest manipulation just to replace SCSI-35 with alternative MPD, because there is no integration of either HLS interstitials or alternative MPD in the broadcast automation chain. So you cannot express this properly with 104 or with 35. And I hope that this is something that will be resolved further on. So we replaced SCSI-35, and it played exactly the same thing, adding a bit of latency. The player used SGAI endpoint and got the ads, and in addition, it got coordinates of a beaconing target that was also using CMCD-V2. It also egressed CMCD-V2 for analytic purposes, and that's how we know that it actually was low latency and how stable it was. So we ran about 50,000 sessions overall in multiple geographies. One thing that completely surprised us, we worked with Google Cloud CDN, and there were no specific optimizations that were actually needed. The latency, the first experiment that we did in 24 was an encoder physically in the BT booth in Amsterdam, origin in London and AWS, then back to Amsterdam, and we were at about 2 seconds there. The result of this year, this is my favorite soundbite so far, were half a second lower in latency than their production DTT. So the production broadcast that goes all over Ireland. So what's next? Okay, first of all, drinks. After drinks, industry adoption. And then there are still a couple of things that we want to improve. First of all, L3D dash measurement and rate adaptation are very different from what you need for low latency dash, for regular low latency dash. So we need to go and play with it a little bit algorithmically. Then an interesting question, what happens if we go and use HTTP2, HTTP3 and priorities? We're just getting started with this. And last thing, I think that in order to make to make low latency stabler, it's good to have special purpose origins that are oriented towards pushing segments and not pushing requested objects. So that's it. Any questions?
Thank you both. Okay, I'm coming.
Mainly out of laziness. CBR or VBR for this play?
VBR.
So in VBR, is there any, have you guys considered using padding of that VBR to get back to a CBR that you could use for things like a national spot? Obviously you have targeted ads, you also have global ads oftentimes and things, or even other ancillary data that you could carry along with that packet, because typically in these transmissions, CBR ends up giving a little bit better experience. So you get what I'm saying? Like, have you guys thought about using padding to get back to a CBR, even though the video is taking the advantage of VBR?
We didn't, and to be honest, I'm not sure it makes sense technically, because it used to make sense when we had UDP and well-provisioned networks. Here we are going over the public internet, even on the contribution hub, and the flow control actually exists, and it's taken care of by TCP or by QUIC. So they're the ones who regulate the rate. You don't have the transport stream case where you had a well-defined pipe. Yes, so we can afford this, and most streaming in any case right now is done in VBR, not in CBR. The reason being this reduces CDN costs, and it's a lot of money.
One more question from the audience? Doesn't seem so. One question from my side. The IBC accelerator demos you did, what was the feedback from the audience there?
From IBC?
Mm-hmm.
People liked it. The first demo, the IBC, the 24 demo, people were surprised that we actually could achieve 2 seconds, which was nice, and it was very network dependent. In places where we depended on wired signal, like in John's booth, it was absolutely impeccable. I just loved coming there. When we're on conference wireless, it looked like a conference wireless. It's absolutely perfect until 8:30 a.m. and after 5:30 p.m.
Okay, thank you. So, saying that, thank you, John. Thank you, Alex. And things are now coming. Thank you for attending today's session. We will have even more technical sessions tomorrow and even more programming on the Solutions Hub.